All right, welcome to the first video of 1.2, atomic structure. So that's a subtopic number 2 in topic 1, materials and their atoms. In this video, we'll be looking at, In this video, we are looking at first 3 science understanding idea that's written here. So all materials consist of atoms. Sure. Atoms are commonly modeled as consisting of elements orbiting a nucleus containing protons and neutrons. Thirdly, emission and absorption spectra of elements provide evidence that electrons are arranged in distinct energy levels and can be used to identify some elements in matter. All right, so those 3 will be covered in here. You don't have to copy these down because they can be found on your lecture note anyway. But you should download the lecture note, and as I go through this video, you should be looking at the lecture note as well. So, start of the first point, the atomic theory. So something that we've spent a lot of time back in year 10 as well. So the idea is that everything, every matter that you can pick up, or even if you don't see it, they are made up of tiny things called atoms. An atomic model is something that's been around. It's been refined many times over the history of the last course of, I guess, 2,000 years, since the idea that we need to be made up of something flexible. So all the spheres are connected to each other. That's the idea that, where the atomic theory actually started. And then people like the Daltons or Rutherford, as well as Bohr, they developed each other's idea, and we came to this model that you see here on the screen. So nucleus is in the middle. It contains protons and neutrons, and electrons are moving around in the places called shells. And if you remember the metaphor in terms of size, is that the nucleus is like very small marble that's sitting in the middle of a sports stadium, and electrons are like audience, one audience in the first row seat, and then B or C levels of seat, there are like a few more people, but they're all separate from each other. They're all apart from each other. What's between them? Electromagnetic field, but virtually there's nothing. It's an empty space in between. And that's a model that has worked to explain a lot of different things, and we are still using it because, again, it makes sense. Now, we can watch the history of atomic chemistry in lesson, and it will spend a bit of time to do question 6 on EW. It's not L, it's Essentials Workbook, page 13. All right, next slide. All right, something about electrons. Now, as I just mentioned, they are located in different energy shells. Some electrons have got lower energy, so they will stay very close to the nucleus. Some of them have got much more energy, so they can climb up to next level, and they'll stay where they are, and third level, and so on. If electrons gain energy from outside, they can jump. Say those people who are in the second level of the shell, when it gains some sort of energy like heat or light, they can be excited, and they might be able to get up to, say, level 3, another shell that's outside. But that's not their normal state. The normal state is called ground state, so it will want to come back to ground state, and when that happens, it has to release some energy. And often this energy is released as some sort of light, which you can measure in different frequency. Say red color light comes out from strontium. That means that that's producing low frequency light, And if you see blue light, that would be much more intense with higher frequency. Okay, that's the reason why you can store more information into Blu-ray instead of CD or DVD, which uses red light. You can also do, I should have gone back to the last one. So flame tests can be done to see what sort of color each element would make. I'm pretty sure you've done it in the past years as well, but we'll try it out and we'll look at emission that it will create with spectroscope, that's the one. You can also use the same sort of principle to what's called atomic absorption spectroscopy, in short AAS. Now, here is a diagram that explains how atomic absorption spectroscopy works. So what you would see is a light source that's producing some sort of light. I'm seeing orange, so let's go that it uses sodium in here. So this lamp is producing orange sodium color light. And that goes through flame, which is like a flame that you can make with in the flame color practical. You can see the samples being sucked up here and aerated and producing that flame. And flame is colored in particular color. Let's say that this sample contains sodium, sodium chloride. And because sodium color light is being, shine onto this flame, which contains sodium ions will absorb a certain part of that light. So the intensity changes. Intensity of light, which was deeper here, becomes a bit less. So much lighter orange color here. That shows that that sodium here was absorbing a particular light with the particular frequency. And through a slit and also some sort of prism, it will then be detected by a photodetector. It measures intensity as well as the frequency, I think. By just sticking to one frequency, you can see how intense the absorption of the light became. And this would also tell you, say, concentration of the sodium in this sample. Or you could also prove that this sample contains sodium. So that's how atomic absorption spectroscopy is used. Right. Different spectra also can be made. If you just look at white color light source, whether that's a LED light or the sunlight, that would have the range of light already. So you would have visible light range from red to blue, or sorry, you should see up to purple or violet. If you are looking at flame color, that can be produced with any different chemicals. So if you light up the salt of it, you can see that hot gas here can be separated into different emission line, which also proves that different electrons in there had different levels of jumping and also how much energy it can release back. So that's a proof that electrons live in a different energy shells and they all have different energy levels. If you use the same chemical that was used to make the hot gas, but you didn't make it into hot gas, so you can let it stay as cold gas, and combine that with a light source which originally had white color. White color means all the range of frequency was already available. And if the light goes through the cold gas and separate it into something that you can see, so through the prism, what you would see is that there will be an absences of lines. So there's no light through that frequency, therefore black color. There's no light through. And you would also notice that the emission line that appeared through the throughout the spectrum would be shown, or where the emission lines existed in the spectrum would be absent in the absorption line, because the cold gas, so the same element that makes up made up the emission is now absorbing all the light, because they can only absorb certain wavelengths of light or emit. So emission and absorption, they are the same thing in terms of, well, from a element perspective. All right. Last part, how are these spectra used? Elements in the sun were identified from absorption lines. Bunsen and Kirchhoff predicted that new elements exist, which happen to be cesium and rubidium. And the presence of unknown elements in the sun, was it mentioned that? Yeah, I think it was sort of mentioned. It was helium, but we didn't know back then. And AAS, atomic absorption spectrum setup, is used all over the world to look at what's in water, how much is in there, what's in wine, what's in whiskey, whether that's going to be bad or good. So quality control is done through AAS. Now we'll spend some time in doing questions 6 and 7 during the lesson, and that's what this is referring to. All right, thank you. That's the end of this video. Thanks for watching.